Okay, so hello everyone. My name is Kunal, and I am your physics tutor. And we are actually doing oscillations. And today is our actual lecture number 11. So let me quickly recap the things कि हमने previous class में क्या क्या चीजें cover करी थी. So हमने previous class में देखा था we learned about the things like compound pendulum. जिसमें हमने ये सारी चीजें डिस्कस करी थी कि इसकी टाइम पीरियड क्या होती है एंड वी रीच टू द कंक्लूजन लाइक इट्स टाइम पीरियड इज एक्चुअली इक्वल टू 2 पाई रूट अंडर आई अबाउट सस्पेंशन पॉइंट डिवाइडेड बाय mg l where l is the actually distance between center of gravity and suspension point, right? So these are the things that we learned in our previous class कि चाहे वो कोई भी rigid body हो, चाहे वो कोई भी rigid body हो, we can calculate its time period if the body is able to oscillate, right? With the help of this formula. Now, in today, and we actually deal some problem also in this. Now, in today's class, we are gonna actually see some kind of vibrations like free vibrations, damped vibrations, and force vibrations, right? So, and the resonance kind of thing that we have to deal in today's class. So, let's start. So, our first topic is actually on vibrations. So, in this, we have to deal with the three kinds of vibrations. The first is like free vibration. Second is like damped vibration. Can I do little bit damped vibrations? And a third is like forced vibration. And in which we have to read a special topic, which is actually known as resonance. So we actually deal today these three topics, right? So let's start with the first one, which is actually termed as force vibration. So what is actually force vibration? So let me quickly set up an arrangement. So let's deal about the free vibrations. What it is, what it is actually. So if you let me recall the first system that we take when we start this chapter, which is actually a single spring block system. So let assume that system. So this is actually our system, and there is a attached mass m, and the spring has a spring constant k, right? So what I'm assuming that if there is actually no dissipative force acting on the system, that means when I pull that mass with the length of x, right? Because there is some actually its mean position. So when I pull this mass and I reach at displaced position sum of x, so we can write the equation of motion as we write earlier also. So equation of actually free vibrations is you can write like restoring force is always equal to minus of k into x. So you can also write mass into acceleration is equal to minus kx. So acceleration is nothing but minus k by m into x. So we reach the equation like we can write acceleration as d square x by dt square and plus k by m into x is equal to 0. So from here we get like omega naught is equal to root under k by m. Right. This is actually our we also called as natural frequency जो हमने previous first या second lecture में ये सारी चीजें cover करी हुई थी, right? Natural frequency. Now, but हमने वहाँ पे मोस्टली हमने टाइम पीरियड निकालने पे फोकस करी थी. हमने इस सिस्टम के बारे में ज्यादा डिस्कस नहीं किया था कि इस सिस्टम में एक्चुअली हो क्या रहा है एंड ऑल. बस हमने ये डिस्कस करा था कि टाइम पीरियड इस तरह के सिस्टम को कैसे निकालते हैं, क्योंकि हमारा जो हमारा प्रीवियस मोटो था वो द थिंग्स इज स्टक टू द वी हैव टू कैलकुलेट द टाइम पीरियड ऑफ द वेरियस काइंड ऑफ सिस्टम, राइट? बट राइट नाउ आवर मेन गोल इज टू फील द सिस्टम कि एक्चुअली सिस्टम में चीजें हो क्या रही हैं, है ना? ये सारी चीजें हमें सीखना है. सो इन फ्री वाइब्रेशन इन विच आई एम टेकिंग द एग्जांपल ऑफ सिंगल स्प्रिंग ब्लॉक सिस्टम, जहां पे दो चीजें हो रही हैं. First, there is no dissipative force. Let me explain this sentence, what it is actually. There is no dissipative force. That means there is no some external force acting on the system. There is no external force acting on the system, which actually, which actually affect the motion of the block of mass m. Right. I hope you'll all understand what I'm trying to say. There is no external force acting on the system, single spring block system, that actually affect the motion, oscillatory motion done by the mass m. Right. So there is actually no dissipative force. If there is no dissipative force, or there is no external force acting on the system which affect the oscillatory motion, so that's the second conclusion we can do is, these are actually conclusions. The second conclusion we can tell is, we have a constant amplitude. The system has a constant amplitude, right? So we can tell in this way that the system has a constant amplitude because there is no dissipative force, or there is no dissipative force, so the system has a constant amplitude, right? So vice versa are true. And we in our first or second lecture we already derived these kind of equations, like how to write the equations and how to calculate the time period if I get the omega naught, which is actually also called as natural frequency, which is actually equal to root under k by n, right? So this is actually is equal to, so we can also so we are also able to calculate the time period, right? Which is actually 2 pi by omega naught. But right now we are not going to discuss that because we already discussed those things. Our main motto is to understand कि vibrations हो रही हैं तो उसमें क्या क्या चीजें हो रही हैं, right? So the first thing we reach the conclusion, there is actually no dissipative force, and the second is the system has a constant amplitude. Now the things is, let me write here the equations. So x is equal to a sine omega naught t plus phi, which is actually phase difference. So this is actually equation जो कि हमने पहले भी डिस्कस कर चुके. Now the second vibration which we didn't know, like damped vibration and forced vibration, ये सारी चीजें हमने कवर नहीं करी हैं. So let's start with the second topic, which is actually our of damped vibration. So what it is, let me give the heading here, damped vibration. So let me quickly set up the system कि actually इसमें होता क्या है. So let's take same system, single spring block system, right? This is actually our system. But right now what I am doing, I am actually submerge this system in this is actually water. You can take any kind of fluid, and this is actually our beaker. So मैंने क्या किया कि जो सिंगल स्प्रिंग ब्लॉक सिस्टम था, ये एक्चुअली देखो यहाँ पे तो फ्री एयर में रखी हुई है, राइट? हालांकि इफ यू ऑब्जर्व द थिंग्स तो एयर रेजिस्टेंस की तरह एक्ट कर रहा होता है इन रियल लाइफ, बट थ्योरेटिकली वी एज्यूम कि किसी तरह की फोर्स नहीं लग रही है, राइट? फ्री वाइब्रेशन में भी some kind of very few, but actually में रियल लाइफ प्रॉब्लम में डिसिपेटिव फोर्स लग रहे होते हैं. अगर आप एक्चुअल में एक्सपेरिमेंट करोगे, सो समहाउ, हालांकि वो नेग्लिजिबल होता है, बट या इट अफेक्ट द सिस्टम एज वेल. नाउ सो इन डैम्प्ड वाइब्रेशन केस में क्या कर रहे हैं, वी टेक द सेम सिस्टम व्हिच इज एक्चुअली single spring block system, but we actually kept the mass m in the, we actually submerge the mass into the water, right? So अब क्या होगा कि यहाँ पे एक फोर्स लग रहा है. In first case there is no external force acting on the system, but in this case there is a force which is actually known as buoyancy force, is actually acting on the system in vertically upward direction, right? That means there is an external force acting on the system which actually affect the oscillatory motion of the single spring block system, right? I hope it will be clear to all of you what I'm trying to say, right? Let me recall again. मैंने बस क्या किया कि इस स्प्रिंग ब्लॉक सिस्टम को मास एम, एम एक बीकर में पानी डाल के उसमें रख दिया। तो अब क्या हो रही है कि जो वाटर है, जो फ्लूइड है, वो एक्चुअली हमें पता है कि वर्टिकली अपवर्ड डायरेक्शन में एक फोर्स लगा रहा होता है, जिसको बाइनेंसी फोर्स भी कहते हैं। तो अब तो हमारे सिस्टम में क्या है कि देयर इज एन एक्सटर्नल फोर्स विच एक्चुअली अफेक्ट आवर मोशन. So that's why what I'm trying to conclude here is we have to write some line here in that there is dissipative force, or you can say resistive force on system, right? What I'm trying to say, there is dissipative or resistive force on a system. So actually amplitude varies because क्योंकि रेगुलरली डिसिपेटिव फोर्स लग रही है तो एम्पलीट्यूड वेरीज करेगा, यहाँ पे एम्पलीट्यूड कांस्टेंट नहीं रहेगा. So the two things we actually the difference between the free vibrations and the damped vibration is कि वहां पे क्या था, वहां पे कोई dissipative force नहीं थी, तो the system has a constant amplitude. But in this case we have a dissipative force, चाहे वो किसी भी तरीके से हो सकता है. We have a dissipative force. So here the system has a actually a variable amplitude, right? So we can say this. Now we are actually define those convert those kind of forces in two terms, which is actually called as a dissipative force. So usko aise likhte hain, which is actually equal to, let me write it here. We can write dissipative force is equal to actually BV. Now let me write it here. What is B and what is V? So actually B is our damping constant and V is actually our velocity. Okay, so this is actually also a force, and dV is actually our dissipative force, or we can call it as a damping force also, right? I hope this thing will be clear to all of you what I'm trying to say. So these are some points that you have to keep in mind. In this system has a dissipative force, amplitude vary, and we actually get to a relation what is actually damping force. So the damping force is also equal to damping constant into velocity. Now let me write the equations of the motions here. So equation of motion, you can write it as like we have restoring force is equal to minus kx, because spring force is actually acting, but there is also a force which is actually known as damping force, right? So we can write ma is equal to minus kx minus b into v. So here we can write acceleration as minus k by m into x minus b by m. We are just dividing the left hand side and right hand side by m and into v, right? And we can also write a as d square x by dt square is equal to minus k by m into x and minus b by m, and we can write velocity as dx by dt, and this is actually is equal to d. Let me write it in a clear way here. Okay, so we can also write it here as a d square x by dt square and plus k by m into x plus b by m into dx by dt is equal to 0, right? But this is actually a differential equation. This is actually the differential equation, right? And we are not here basically focused to solve this differential equation, but our main motto is to uh, go through the solutions. What is the solutions of this differential equation? Let me write it here. Our motto here is to look only its solution, not to solve this equations, right? Not to solve this equation. Our motto is to just to look at its solution. What is its actually solution is. We don't have to solve this, right? So on solving what we get, we get actually in later class you will learn like how to solve. So we have to take a trial solution here. So x is equal to something a cos omega t, and then you solve, then you get the final answer. So what we get here, we get the omega dash, or you can say omega dash. Yeah, it will be fine. It is actually is equal to k by m minus b by 2m whole square. So this is actually omega after damping, because look at here, why our omega is changes. So the reason is because we don't have the same frequency each and every time. Each and every single time, each and every single time, each and every single time, we have actually continuously acting dissipative force. So it affect our amplitude, it affect our omega. So its effect automatically affect our frequencies. So what I'm trying to say, uh, we have actually a constant kind of frequency, but it's actually a different from the natural frequency. So what it is actually, you can write it as like omega square is equal to omega naught square minus b by 2m square. You can also write in this way, right? So this is actually our uh, damping. Let me write it here, omega dash, otherwise, or omega 1, whatever you want, you can, right? So here we can write x is equal to a sine omega dash t plus. So this is actually our equation of. So let me tell you again. Let me recall the again कि हमने क्या क्या इसमें देखा. तो देखो, the thing says कि ये जो सिस्टम है, इन इन डैम्पिंग वाइब्रेशंस, इन डैम्पिंग वाइब्रेशंस, हमारे पास क्या होता है, हमारे सिस्टम में एक कंटिन्यूअस फोर्स लग रहा होता है ना. तो उसकी वजह से क्या होता है कि एम्पलीट्यूड सेम नहीं रहता. द फर्स्ट थिंग यू हैव टू नो. एंड हमारा जो फ्रीक्वेंसीज होती हैं वो भी डिफरेंट होती हैं, राइट. दैट मीन्स क्योंकि ये फ्री वाइब्रेशन नहीं कर रहा ना, लाइक इन फ्री वाइब्रेशन केस we have a different equation of the motions, right? But and in damping case, we have to consider the damping force also. So we have a different kind of equation. So we have a different solutions. So that's why what I'm trying to say, we have a different omega, different frequency, and a variable amplitude. Now we write the equation of motion here, which is actually is equal to Fr, basically restoring force, is equal to minus of Kx, which is actually the spring force, and then minus of Bv, which is actually the damping force. This is actually damping force. Now I'm writing the this restoring force as mass into acceleration, right? I'm writing this force as mass into acceleration, and then I write, and then I divide it by m by both sides, and then I write the acceleration equal to d square x by dt square, and v is equal to dx by dt. And again, I am here telling you the main thing. You when you go to the college, you learn how to solve this differential equation. Actually, we have to take the trial solution. In this case, we have like x is equal to you can take a e to the power I alpha. Basically, it's a, like you have to take the trial solution and you have to solve this. And on solving, you get relations between the omega damping in case of damping and the natural frequency. And that the relation is omega dash square equal to omega naught square minus b by 2m whole square, right? So, okay. And we get the relation which is x is equal to a sine omega dash t plus phi. So this is actually our equation of motion. This is actually, you can call it as dynamics, right? Now, the next thing that we have to talk about is here something we have to talk about is amplitude. Like मैंने आपको स्टार्टिंग में कहा कि we have a variable amplitude, right? Because as time passes, our amplitude changes, and after certain time, it becomes zero. है ना, कुछ समय के बाद हमारा सिस्टम जो है वो ऑसिलेट नहीं कर रहा होगा. So how to calculate the amplitude? So here we have to calculate, we know, like we have to know how to calculate the amplitude. So let me write it here, amplitude. of amplitude of damped vibration, right? Okay. So the amplitude of the damped vibration is actually exponentially decay, right? So let me write it here direct. A is actually varying, like A naught is our the initial amplitude, A naught, e to the power minus bt by 2. This is how our amplitude varying. This is also called as exponential, right? So this is how our amplitude actually varies, right? I hope it will be clear to all of you. And let me mark it here. Our A naught is actually initial. Okay. So this is how our amplitude varying, actually exponential decay. Our amplitude is varying like A naught e to the power bt by minus bt by 2. And you have to, if you look the graph of A versus T in damping vibration. So it something look like in this way. Okay, let me make it in a clean way because I think I have to insert. Okay, that's fine. So let us consider this axis actually representing the A, and this axis is actually representing the time. So this is actually our amplitude at time t is equal to 0, right? And it's actually dk. So it's something like this, right? So this is actually the graph between uh, A versus T. Now, let's solve a question based on this. So there is actually a question. So question number 1. Okay. So you have to find like time after which amplitude becomes half of initial. Okay. So you have to find like time after which, uh, okay. So you have to find like time after which the amplitude is actually the half of the initial. So we all know that in case of damping, obviously we are talking about the damping vibration. So we know that at the time t is equal to 0, we are assuming like our amplitude at A naught, like A is equal to A naught. And we have relations between the amplitude at this some time t is equal to t. So it is actually A is equal to A naught e to the power minus bt by 2. A is equal to A naught exponential e to the power minus bt by 2. Right. So this is actually our equations. And the things given is you have to find the time when the amplitude is actually the half of the initial. So A is actually our half of the initial, which is actually A naught by 2, A naught e to the power minus bt by 2. So this and this get cancelled. Take the log both sides. So it will be like ln 1 by 2 is equal to ln e to the power minus bt by 2. So we can write here ln 2 is equal to ln e to the power bt by 2m. Actually 1 by bt by 2m, it will be same, right? So it will be 2 is equal to bt by 2m, right? I hope it will be clear to all of you. ln 1 by 2 actually. Or you can say ln 2 is equal to bt by 2m, because we are using this thing like you from log property, right? I hope it will be clear to all of you because the base of the ln and the this thing what it's called power is same, so it will be actually interchange itself and it will be will get bt by 2. So our time taken is actually 2m by b ln 2. So after such time our amplitude is actually the half of the initial, right? So you have to keep this thing in mind. After how much time our amplitude becomes the half of the initial. So it is actually 2m by b ln of 2. And in question, actually, you have mass and damping constant is given, right? So you are easily to calculate. Like if I'm going to tell you take the mass is equal to 10 gram and B is equal to some 5 into SI unit. Right. So you are able to calculate the value of time. कितने समय के बाद amplitude आधा हो जाएगा, right? Please give me a moment. Okay, sorry for the delay. Actually, there was a call. Okay, so where I am? Okay, so I'm telling you कि वहाँ पे आपको questions में mass and ये इसकी values दी हुई होंगी, so you can easily calculate this thing, right? Now let's talk one more thing, which I'm talking about energy of oscillator. Actually, when I'm talking about the energy, so it will be I'm talking about the total energy. So we all know that our energy is actually half of Ka square, usually, right? Total energy of this kind of system. So here the amplitude is actually varying as we have a relation of amplitude A naught e to the power Bt by 2m. So we can write here E is equal to half K A naught e to the power minus Bt by 2m whole square. So when you do so, what we'll get? We'll get E is equal to half K A naught square e to the power minus Bt by m. Right. And we all know that this expression is actually the energy for free vibration. जब यहाँ पे कोई dissipative force नहीं लग रहा था, so we have a energy of this system. We actually already calculated the all kind of energy, and we get the for single spring block system we have a total energy is equal to half of K A square. Right. So we can write here, we get another relation here, which is actually E is equal to, we can write E naught e to the power minus Bt by n. That means our energy is also actually, this is actually exponential decay. So our energy is also varying. It's not constant in damping, right? In free vibration, our energy is constant. Total energy is constant, which is actually is equal to half K A square. But in this case, our energy is not constant. It's actually decreasing. And how it is decreasing? It's actually exponentially decreasing. Right. And let me write it here, which here E naught is equal to half of Ka square. Okay. Now let me draw the graph of E versus T. So obviously it is actually the exponentially decay. So the graph will be same as. So the graph will be same as U. Okay. So actually the graph will be same as we have a E naught half of K square and it's continuously decreasing. Right. So this is actually the graph of E versus of T. I hope you will we will done a lots of discussion in डैम वाइब्रेशन, जैसे जिसमें हमने उसके एम्पलीट्यूड पे बात करी, उसकी इक्वेशंस पे बात करी, है ना, एंड उसके ओमेगा पे बात करी कि जब किसी भी सिस्टम में अगर डैम्पिंग लग रहा हो, डैम्पिंग फोर्स हो, तो उसकी ओमेगा चेंज हो जाती है. इट्स नॉट लाइक द नेचुरल फ्रीक्वेंसी, राइट? इट्स एक्चुअली चेंजेस. So these thing, and we talk about its energy and all. Now we are moved to the next topic, which is actually the third one. It is actually forced vibration, in which we have to talk about the resonance. Okay. So let's move to the third topic, which is actually forced vibration. So let me give you a very fair example of this. If you, अगर आपने कभी जिम वगैरह में गए होंगे, तो वहां पे क्या होता है कि देयर वाज अ रोप जिसको आपने एक एंड को पकड़ के उसको ऐसा ऐसा कंटिन्यूअसली जो ट्रेनर होता है या फिर जो जिम कर रहे होते हैं वो कर रहे होते हैं, राइट? लेट मी टेल यू व्हाट आई एम ट्राइंग टू से, और लेट मी tell you in some other way so you can understand what I'm trying to say is. Okay. So what I'm trying to say is कि let's take with the same example, spring block. वैसे जैसे आपने वो देखा होगा ना जिम में कि वो एक रोप पकड़ के ऐसा ऊपर नीचे कर रहे होते हैं, राइट, रोप को, और इस एंड पे कंटिन्यूअसली वो फोर्स लगा रहे होते हैं अप्स एंड डाउन, राइट? तो वो एक्चुअली जो कंटिन्यूअस फोर्स जो लग रहा है सिस्टम पे ईच एंड एवरी सिंगल सेकेंड, सो दैट इज एक्चुअली we are creating we are applying a continuous force uh, to continue the vibrations, right? So let me tell you with the same system, which is actually a spring mass system, right? You can consider it with this too, but let's start with the spring mass system. Spring, spring mass system. So what I'm trying to say is, let us suppose this is actually our spring of mass and what I'm doing here is, and this is actually our main position, and what I'm actually doing is I am continuously applying a force F naught cos omega t. Let me call that. I am continuously applying a force on this. Why it is varying cos omega t? Because it's also under the influence of the spring force. So what I'm trying to do, I am continuously applying a force on the system, which is actually varying at F naught cos omega t, right? This is actually F is external driving. Okay, so our F is actually external driving force, which is actually continuously acting on the system, right? Or you can say F naught sine omega t, any like cos or sine you can comfortable with, you can call it as, right? Now here few things happening. Let me write here. System in steady state. I'm not talking about the transition state or initial state. I'm just talking about the steady state. So system oscillates with frequency of external amplitude, external force. And the second thing say here is our amplitude is constant. So the thing says we have in forced oscillation, we have a constant amplitude and there's a continuous actually force acting on the system, external force acting on the system, which is also called as driving force, right? जैसे यहाँ पे damping में क्या हो रही है ना, देखो look at it, let me tell you, जहाँ पे मैंने फिगर बनाया, देखो डैम्पिंग में क्या हो रही है कि अगर ये स्प्रिंग, अगर ये मास अगर ऊपर जा रहा है इस वाटर सरफेस से ऊपर जा रहा है, सो देयर इज नो डैम्पिंग फोर्स एक्टिंग ऑन द सिस्टम। जब वो फिर से नीचे आ रहा, देन फिर से बाइनेंसी फोर्स लगनी स्टार्ट हो रही है। पर जैसे ही ये पानी से ऊपर जा रहा, फिर बाइनेंसी फोर्स लगना बंद हो जा रही है नहीं है? But in this case, we have a continuous acting we have continuous acting of the driving force, which is actually equal to F naught sine omega t, right? And here in this case, our actually amplitude is constant. So let me write the equation of the force vibration here. And now what I'm trying to consider, if I'm considering let us consider the damping also here, right? So make the problem interesting. We have a damping. I'm creating a damping situation here also with a damping constant, obviously V and so if I write the equation here, so how can we write? Okay, so we can write here as F restoring is equal to minus Kx minus dV and plus F naught sine omega t. This omega is actually the omega of forced vibrate, right? The external force, the external driving force, this angular frequency is actually the external driving force omega, right? So let me write it here as a function of acceleration. So acceleration is equal to minus k by m into x minus b by m into v and plus f naught sine omega t by m, right? So we can write here. So again, I'm trying to tell you our motto is not to solve the differential equation, but to just to analyze its solutions. Plus b by m, we can write v as like dx by dt minus f naught by m sine of omega t, right? And this is actually is equal to 0. So when we solve this equation, we get x is equal to a sine omega t plus y, right? Omega is same as the omega of driving force, right? So here we can write the And then the amplitude is constant. And what it is, so we can write here the amplitude also. And the amplitude is actually here is equal to f naught by m. You have to just remember the formula, or it will be like yaad bhi ho jati hai. So don't worry about that. Omega minus omega naught, omega square minus omega naught square. And I hope you all remember what is actually omega naught square. So omega naught is actually our angular frequency plus b by m omega square. So this is actually the amplitude. Right. So this is actually the amplitude of the system. Let me write it here. What is actually omega naught? So omega naught is still our k by m. And what is omega? So omega is actually angular frequency of external force, external driving force. Okay. So this is the thing that I want to tell you. Right. Okay. So let me recap once again. So what is actually force vibration is? So the force vibration is nothing but we have a continuous external force acting on the system, which actually affect the motion of the basically which affect the oscillatory motion of the system, right? So few things that you have to keep in mind. The first thing is like system oscillates with the frequency of the external force. We are actually talking about the steady case. And the next thing is actually amplitude is constant. And when we write the equation of the force. So we are actually writing the restoring force is equal to minus kx, and we are actually also considering damping here. We actually introduce the damping by keep the fluid in a bucket. So there is actually the damping. So when I write the equation, and I'm again telling you, our motto is not to solve the differential equation, but to analyze its solutions, right? So we get to the equation of motion, which is actually equal to x is equal to a sine omega t plus phi. And here the amplitude is constant, and what it is, so our amplitude is actually we get the amplitude by this formula. Okay. Now we have to learn the next thing, which is actually termed as resonance. So what is actually resonance? So resonance, it is a condition. Let me write its definition first. So it is actually a condition of maximum amplitude, right? So it is actually the condition of the maximum amplitude, and ये होता कब है? It occurs when omega naught is equal to omega, or you can say omega is equal to omega naught. Look at here. We have the amplitude in case of damping. We have actually F naught damping plus force vibrator is actually omega square minus omega naught square का whole square plus b by m into omega square, right? So if if I we have a maximum amplitude when this term becomes zero, right? So because see we have a b and b by m and into omega, and our b is actually damping constant, so it is actually very less in value, right? If you solve the problem, so you get to realize that we have a very actually least value of b, right? So so what is actually resonance? So resonance is a condition when we have a maximum amplitude, and when it occurs, so it occurs when angular frequency of driving force is actually equal to the natural frequency of system. I hope it will be clear to all of you. So I think that's all for today's, and tomorrow is our last class on the oscillations, in which we are gonna deal with superpositions and waveform. Okay, so okay, that's all for today. Thank you.